All right. So 20.2 grams of an unknown carbohydrate combusts into 12.12 grams of water and 7.29 liters of carbon dioxide at 40 degrees Celsius. What is the empirical formula of the carbohydrate? Okay, so first of all, there's a lot to unpack here that we need to immediately do before we even start thinking about what the answer is. So, first of all, unknown carbohydrate. What's a carbohydrate? A carbohydrate is some combination of CH and O, not another C. CH and O, some combination, X, Y, Z. And it combusts, so that means we're going to have oxygen into, so now we've switched over on the other side, 12.12 grams of water plus 17.29 liters of CO2 at 40 degrees Celsius. So this is going to be our preliminary chemical equation that we're going to use to try to solve this. We are trying to solve what are the X, Y, and Z here. We need to know what the empirical formula of that carbohydrate that we're talking about is. So we need to figure out what they are based on just the values given to us. I forgot to mention 20.2 grams over here. So how do we even begin with this? So luckily, I can consult my rule book here that I made for solving problems like this, where you're trying to find an empirical formula of an unknown thing given only values. The first step says find the amounts of each compound necessary in desired empirical formula. So first it tells us we need to find the amounts of this, and this in our empirical formula. And you'll see in a minute, this actually doesn't matter because we're just trying to find this over here. And there's an oxygen here and an oxygen here. So we only want to know about this oxygen, this hydrogen, and this carbon. So we want to convert all of these measures here into grams that we can use. So this is already in grams, so that's good. This is already in grams, so that's good. This is in liters at 40 degrees Celsius. We need to change that to grams. So this is a simple gas stoichiometry problem where you say pressure times volume is equal to the number of moles times this constant, and then temperature. So we want to find how many moles there is so that way we can convert the amount of moles into the amount of grams that we need, because we want to convert all of these to grams, because that will help us with our next step. So we're going to say pressure. It doesn't specify any specific pressure, so this is 1 atmosphere. Volume, 17.29 liters. Number of moles, that's what we don't know. That's what we want to figure out. This constant here is 0.0821 because we're going to try to solve this over atmospheres, liters, and Kelvin, and moles, of course. So question mark moles. And then this temperature here is 40 degrees Celsius. But if we want to convert that to Kelvin, because this constant only works when you're in Kelvin, we have to add 273 to this. So that would be in degrees Kelvin. So now let's just plug everything in. First, let's just isolate this moles here so we can just plug it in and then instantly get an answer. PV over RT, because we just divide over the R and the T. And now N is equal to, and you'll have to show every single step if you want to get answers right on the AP test and on tests, especially if you have an overbearing teacher or overbearing grader. So P1 atmosphere, and you want to show the units on everything, except for this constant. We don't need to. That's kind of implied by the fact that you're using atmospheres, liters, Kelvin, and moles. So N moles, this here would be volume, so 17.29 liters, all over 0.0821 times 40 plus 273 is 313 degrees Kelvin. Okay? Now we just take a calculator and plug it in. So 1 atmosphere times, I'm going to bring this closer to you guys, which means I have to get up, 17.29 liters, all divided by 0.821 times 313. I was able to skip over the atmospheres because it's 1. is equal to 0.672 nonsense. And so this would be number of moles, but yeah. So number of moles is equal to 0.67283. And I'm going to round everything off to 5 decimal places to begin with, even though our sig figs over here tells us that we should round it off to 2 or should round it off to 3 with our answer. Because then we would get more exact data if we use more exact numbers. There's no need to round it off midway through, because if we keep rounding it off midway through, it's kind of like this domino effect where your margin of error begins here, and then if you multiply it again, it gets even bigger, multiply it again, it gets bigger, 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 until you have a genuinely different answer. Because there's a lot of calculations, especially in a problem like this, where just being exact with your calculations up until you have to round for sig figs, when you have your completely final answer, that's when you would round off. It would prevent errors. So now this is the number of moles of carbon dioxide. Now let's convert this number of moles into grams. And this is moles of carbon dioxide at STP, because we just converted it with this equation. So now let's do carbon dioxide, which is 44.01. Oh, I went the wrong way. 44.01 grams of CO2 times 1 mole, or over 1 mole of CO2, not times. So we'll multiply this number, and it's really nice if you have the answer key or a way to use a calculator that gives you the answer here, which means we wrote down the whole thing, but it's not necessary because we can just pull it from the previous answer and plug it in. Times 44.01 is equal to 29.6113. I'm going to say 6114 because 9 is a number very close. So 29.6114 grams of CO2 is what we have. So really, I can erase this kind of, because I don't really care about what it is when it's not at STP. So this is 29.6114 grams of CO2. Okay, so now we have everything converted into grams, which means we are done with that first step. Now our second step, which is probably the most important step, says multiply the amount of compound, so amount of any of these, by the percent of desired individual element per compound to get the amount of element. So let's deconstruct that again. Basically, what we are trying to find right now is the percentage of, or is the amount of carbon, the amount of hydrogen, and the amount of oxygen. So if we're trying to find those things there, that means that we need to split up these into individual hydrogen, oxygen, and carbon, kind of as if we were to say, like, this is how many grams of hydrogen, plus this is how many grams of oxygen, plus this is how many grams of carbon we need. That's kind of just like how it would go, because then if we have exact grams, we can just translate it over to the other side way easier. We wouldn't have to deal with other stuff like this. And there's a special way we have to do the oxygens one, because the oxygens here is present in both of them. So I'm going to kind of show how we're going to do that right now. For now, let's ignore oxygen. So I'm going to create a dashed line between the two, because one property of how chemical equations works is that mass is conserved, or elements are conserved on both sides of the equation, which means however many grams of hydrogen are over here is going to be equal to how many grams of hydrogen are over here. How many grams of oxygen here has to be equal to how many grams of oxygen here. How many grams of carbon here has to be equal to how many grams of carbon here. So notice that the only thing here that has hydrogen in it is the water. So we can multiply the amount of hydrogen per water molecule, which would be 2 times 1.008, because this is the molar mass of hydrogen, times 2, because there's 2 hydrogens, divided by, not that, 18.016. This would be grams of hydrogen per gram of water. Basically, this is just saying this is how many grams of hydrogen per gram of water. And this here would give us the percentage of hydrogen in the water. So the percentage of hydrogen in the water is just a ratio. We need to use this ratio to figure out how many grams of hydrogen there are present in our specific equation, which means that we would have to multiply that by the actual amount of water. So if we multiply that by the actual amount of water, we would get some answer, but we have to multiply it by that first. So what I'm going to do is create another little column where we multiply it by 12.12 grams of H2O. And then we don't need to multiply by anything else down here. This is Na. So then we can say now 2 times 0.110 or 2.1. Yeah, you see, I don't need to narrate it out and make myself look stupid, is equal to that. Multiply that by 12.12 because this here's the ratio percentage of how much hydrogen is in any given water molecule. Then we need to multiply by the amount of grams to tell us how many grams of hydrogen there are present on this side of the equation. And just note that even though we're talking about just the water, multiplying it by this will give us the amount of total hydrogen in the entire side over here, because water is the only thing that has hydrogen in it. So if this other thing over here had hydrogen in it, we'd have to include both of them, which would mean we'd have to average out the ratios and do something really stupid. So we're not going to do that. So now that would give us 1.356 grams of hydrogen in our equation in total. So now just remember how I said ignore oxygen for now. The reason why we have to ignore oxygen is the same reason why I just said this only works if there's only one compound that has the desired element in it. Because notice how oxygen has it in both this one and this one, which is a big issue. Because then that means we have to, like I said, average the ratios, do something really stupid, average the amount of each thing, which would just be extremely annoying and completely unnecessary when there's a shortcut method that I'll show you later. So we're going to ignore the things that are present in both for now, and then we're going to skip over to carbon because carbon is in just carbon dioxide. So that means we can tell how much carbon is in both this side and equally this side, because remember that property that says the elements are never destroyed, just based on how much carbon there is present in this carbon dioxide amount here. Okay, so this is how many grams of hydrogen, so I'm going to give this a little bubble. Okay, now we're going to have this here. First of all, we need to find the percentage of carbon per carbon dioxide. So we're going to go 12.01 grams of carbon per 44.01 grams of carbon dioxide. Now, I just have these two numbers memorized because they appear so often, but if you don't know where these come from, it's just the molar mass of each of these things that you can pull just by adding, 12.1 plus 16 times 2 gives us 44.01 grams of carbon dioxide, because 1C, 2 O's, simple as that. Water is the exact same thing, but with the different elements. So that would give us here the percentage of carbon per carbon dioxide molecule. That's what that gives us. But now it's a ratio, so we need to multiply it by an actual amount to get an actual amount. And the actual amount we need is this 29.6114 grams of carbon dioxide up here. So now what we can do is multiply both of these two together. 12.01 times 44.01 times 29 points. Actually, you know what? I'm going to go back because this calculator is cool and I can just select this thing here and put it there so I can get an exact number. Because again, we don't like to round off until the very end. Is equal to 8.081 approximately grams of carbon. So that's how many grams of carbon are present in the whole thing, and now we're missing just one. We're missing this oxygen number. And the oxygen number is actually a lot simpler than you might think it'd be, because you may think that how I've told it from before with all of these things up here, that you have to do some nonsense, but you actually don't, because it gives you the amount of unknown carbohydrate, which means that if the only thing that has hydrogen and the only thing that has carbon are the carbohydrate over here, this thing minus those two things is going to give us how much oxygen is present in just the carbohydrate. I mean, makes sense. This is how much carbohydrate there is. This is how much hydrogen there is present in the entire equation. This is how much carbon is present in the entire equation. What would be left over from the difference between that, and that is how much oxygen is present in the whole thing. So we'll go 20.2 minus 1.356 minus 8.081, and I'm going to specify this as grams of carb. This is grams of hydrogen. This is grams of carbon is equal to grams of oxygen. Let's just plug it in. 20.2 minus this thing up here minus, let's scroll back till we find the 1.356 right there, is equal to 10.763. 10.763 grams of oxygen. Okay, so now that's how much of each of these things are present in that. So these two, oh, there we go, there's my fingers. These two there are present in the entire equation. This one is present just in the carbohydrate we're talking about, because this oxygen here is present in both of these. So this is only representative of that. So please don't get that confused. But then in essence, these two are also present in the entire equation because the only thing that matters for it is this. Okay, there we go. And if you can see, I'm actually experimenting with the whole using my fingers really close to the camera, because just by looking up at the camera, I can see it. So that's how many of those are present, and I'm just erasing it so I can get more space. Okay, so that's step 2 done. Multiply the amount to get the percentage of desired individual per compound to get amount of element. We got the amount of element in each of our things here. So I'm going to give this a little bubble. Okay, now the third step is convert the grams of each element, convert these things to the moles of each element. Oh, that's really simple. So we'll just go 1.356 grams of hydrogen multiplied by the ratio. So 1.008 grams of hydrogen from the periodic table is 1 mole of hydrogen is equal to some number. And then we'll go 8.081 grams of carbon multiplied. So 1 mole of carbon is equal to 12.01 grams of carbon. And then we'll go 10.763 grams of oxygen is equal to 1 mole of oxygen over 16 grams of oxygen. And then is equal to. So now we'll just plug everything into our calculators. 1.356 divided by 1.008, that's 1.001. Don't do that. 1.3452, we're going to round this one off to the nearest placement that's closer to 0. So this 8, we're probably going to round it, or no, we'll round it off with a 0 because it's literally a 0. So 1.345238. Okay, just try to be as exact with this number as you possibly can. So that would be then moles of hydrogen. And now because we've counted all of these 3 things here, let's just go ahead and erase this so I have more space. So that's moles of hydrogen. Now we'll convert it. 8.081, let's read numbers, divided by 12.01 grams of carbon. That's how many moles of carbon there were. Notice that that's the exact same thing we had before at the very beginning, moles of carbon. Or I think, no, what we had before was moles of carbon dioxide. I think it's just a coincidence that those two happen to become a very similar number. 856 moles of carbon, just rounded off to a nice number that's very far down the list of decimal places. So now 10.763 divided by 16 is 0.6726875. Notice it's very close to the other number, not a coincidence. 0.6726, we'll go 69 moles of oxygen. Okay, Now, which of these three, oh, well, before we go, before I start talking about that, let's just talk about what the final rule is. Divide by the smallest number of moles to get the number of atoms in the empirical formula. Well, that makes sense because these three here were the amount of grams of each element present in the entire thing up here. So if then we divide by the number of moles and the smallest number of moles, we'll get some number that's equal to the amount of atoms in the empirical formula, which is just what we've done for so long. So 1.34523 divided by some number that's the smallest. Let's find which one's the smallest. The smallest one is this one down here. So 0.67269, 0.67269, 0.67269. These two are so close to one another that you can automatically tell that that's one, and then this would be 1C, this would be 1O. And now this final one, if you can see it just based on math, props to you, but this is going to come out to be about 2. 2 hydrogens, which means the entire thing is CH2O. That's the entire empirical formula. And now just note that those steps are all there so you can see them. That is how you do it. Oh my God, there's so much work involved in this one problem. 21 minutes. I was able to explain the entirety of how derivatives work in half that time. Oh my God, that's ridiculous. Okay, there we go. And also, if you're wondering where I got this problem from, in case you want practice, I actually got this problem just based on a known equation that I know, which is glucose. Because if you want to find the actual molecular formula of what this is, you can't find it based on the information I've given you up here. But basically, I just took glucose plus oxygen is equal to water and carbon dioxide, which is something that I've known since like taking bio in 6th grade. So all I did was just actually solve for the thing and then I put in a random number for how much of this is there, and then just actually reversed it around to find how much of each grams there were, and then made it a little bit more complicated by taking the amount of carbon dioxide out of STPs just for demonstrational purposes on how you would deal with stuff like that. So that's literally all I did. I didn't find that problem from anywhere. Because it's so specialized what these things are that it's extremely difficult to look up the problem. So yeah, that's all I did was I just made the problem myself. And that's why I'm only going to do one of them because they take freaking forever. Okay, there we go.